in a GitHub directory, who's using GitHub actively? And the rest knows of GitHub? Yeah, a bit. It's a version control website with your code. So, right, you seem familiar with that. It loads all the commits from there, and it loads the analysis files from there as well. So if we open up the project, then, and let me quickly close the one from the previous session, and there we go. Then basically this is what a pipeline looks like for me. And what does that mean? Well, at the very beginning of a pipeline, you might start with realigning some functional scans. And well, if you click on that, you might want to set a path to those functional scans, and you might want to say, well, this is where I want the mean of those functional scans to be saved. So this is the moment where I hope that you manage to connect to the server. So that's what we're gonna test for like right now. Let's see if I still know that password. Yeah, there we go. So if you go to the home SCATRAID share CDRF 2009 hands-on data, then you see some data that I put there from vanMourik. And you'll find two folders. One is single subject, one is group data or something of that kind. That single subject is really the end-to-end analysis of a single subject. So let's see, where am I now? Right, I'm in one folder above. And the subject 11, the reason that I shared subject 11 with you is that that is my brain. So it was easier with, you know, privacy issues and permissions. And where am I? What you can see is that the file path I had right here, scans functional, mean functional, is a file that's actually here on disk. So if I use FSL view or something like that. Let's see, how do I open FSL view? Does somebody know that by heart? FSL is apparently here. No. But it looks like there is already an FSL here. Maybe. Let me quickly check this. Okay, so if I source my, where is it?
It's /home.
In /home /scatraid. Oh.
Share.
Share.
CDRF 2019.
Yeah. Software.
There's a tools.config file there.
There is a tools.config.
Yep, and just hit enter, that'll set your path so it points
yeah.
to FSL, etc. And then server and everything else.
Brilliant.
It says it's out of the MATLAB 2017 Meteor paths.
Nice.
It's lying about that.
Oh,
I'm not sure why. I'm still working on that. You might still have to manually add them. But conceptually, that gives you the FSL, everything you saw ahead of time.
Brilliant, thanks.
So I'll add that list up
yeah,
here.
That wasn't
but that still no guarantees that FSL works for you, but now you're FSL terrorist.
But at least now we can quickly see if I use FSL view on the file we just checked out, scans, let's see, and it was in functional, mean functional. There we go. And maybe we need to set this slightly. No, there you go. That's my brain. Only in occipital slides because we're only interested in the visual cortex. But the point is, not so much like this is my brain, but the point is that this application allows you to drag and drop functions for, well, anything, if it's for registration or for pre-processing. For example, if I only have DICOMs and no nifties yet, to add it and to drag and drop, to connect the inputs and the outputs such that the analysis script is automatically generated. So this, what you see here, is automatically generated code that is directly runnable in MATLAB.
How did you open the window?
How did I open this window?
Yes,
right. Okay. So here in the browser, there is just this little box, and let me quickly take that one and delete it again. Anyway, but the point is also not so much that you can do a realignment. The point is that this is the entire analysis. So with the previous group, we went into the registration process a bit more. So basically, what I show there is that you can use boundary-based registration, and after that, you can do some non-linear version of that. And it's very well, briefly explained here that you can do a non-linear version of boundary-based registration in order to correct distortions in your EPI. And one of the things I'm quite adamant about usually is that it's very important to save the intermediate well, output of those files to something that is very easily inspectable. We had a short discussion about, well, what is good enough in terms of distortion correction. My opinion is that whenever you don't know when something is good enough, at the very least, you can write a pretty file, like a little movie file with boundaries. I think I'm quickly going to show you that one. But that you can show a file like that such that you know what kind of decisions you made and based on what. Is there anything specific?
I'm getting ready to take notes on how you're going to look at that movie file.
Right, okay.
Just looking for board space or looking
okay,
at that movie file.
Cool. So, well, let's check that out. There is this little movie function. And what does it write? Well, there is an output that is a registration movie, and it is in co-registration/bbr.avi. So I think a moment ago we found an application with sound and video. Video. Oh, right.
Okay,
and
it's. I was looking down again.
Right. Sorry. And on the sound and video, there is a videos application. Okay. And this one is fortunately already pointing to the right path. Well, and you can try this yourself if you want to. If you just open a file here, you can move to the subject 11 slash co-registration/BBR, this path. And what you'll see is this little file. The take-home message, oh, sorry. Let me start that from the beginning. So that's just a file of the functional scan with the free surfer boundaries on top of that. And you could, if you want to, run another co-registration step, or like this recursive boundary registration, for example, and output a similar file like this. The take-home message is it's very useful to have some intermediate quality control steps. I'm going to close this again and then move on. Because, yeah, my apologies, but we already discussed the details of recursive boundary registration in the previous group, and we noticed that we didn't have time to go through everything. So we're going to move on with the layering and the question of how to obtain a laminar signal. So this morning, John taught us a little bit about that and also about the history of obtaining laminar signal and the way in which I already drew a cortex, the way in which you can do that in different ways. So suppose I've got a cortex, I can just draw lines from one side to the other and at different points interpolate the volume. And there are different ways of well, drawing intermediate surfaces. And one of them was, according to the equivolume principle, the idea that if you're in the, oh, sorry, let me do it this way. The idea that if you're in the inner curve, the thickness expands a little bit, and when you're in the outer ring, it shrinks a little bit, like this.
Sorry.
What's
So we can capture your board.
Oh yeah,
so I'm just going to move.
Brilliant.
Sorry, you're just going to watch yourself draw.
No, that's fine. That's fine. I'll do that. And what you could do with these intermediate surfaces is, again, just going from one side to the other and interpolate your volume at different points. But there is a different way. One of the problems with this way is that you get some inherent blurring and some leakage from one layer to the other, because a gyrus always lies inside a voxel grid. So let me quickly draw a voxel grid here. I'm just gonna draw something like this. If I go from one side to the other here, well, then the signal here will be some, well, you can do it in different ways. I can use a nearest neighbor interpolation and say, well, my signal here at this point is always just exactly the one, the signal intensity of this voxel. A different way is saying, well, let's use some trilinear interpolation. Let's just use some weighted average of all the neighboring voxels, or even some sinc or spline interpolation. Anyway, either way, whatever you're doing, you will get some signal from other voxels. But those voxels also lie in different layers. So ideally, you wouldn't necessarily interpolate. Instead, you would like to separate the layer signal. Now, is there a way of doing that? Well, there is. This problem is quite standard in fMRI, but then in the temporal domain, because what you're doing in a pretty standard temporal regression is saying, right, I know that my one output signal is a linear superposition of different stimuli, and you're trying to invert that system by means of a temporal regression. And a similar thing you could do, but then in the spatial domain. So that's one of the ways in which we can try and describe this. We could say, well, this voxel here, Cheryl, do you have different colors for me?
I do. There's a bunch of colors in the drawer right in front of you, so if you don't like.
Any color.
Right, and there's more down here.
Perfect. So we could say, well, let's now grab this one voxel here and say, Well, which of these of the layers are represented in that voxel? Well, there is a tiny little bit of this one. Let me grab a different color for that one. Maybe there is some 5% of this layer, and well, some 40% of that layer, and then some, I don't know, 25 of your third layer, and then there is still 30 left for your CSF. Now, in this case, I've got three different layers, and on top of that, I've got a CSF layer and a white matter layer, and that basically gives me a column of, let's call it a beta. We're just going to use beta weights in the same way as you know them from temporal regressions. And there is a white matter signal. And let's just, at the moment, call them layer 1 and 2 and 3, which is not identical to the histological layers in any way. This is just for clarity right now. Oh, sorry. And the CSF layer. And we can represent that as a vector. And in the same way as a temporal regression, well, can I talk about my voxels as my signal, as my Y? So there is voxel 1, voxel 2, until voxel n is equal to, well, that those numbers, those percentages that I just came up with, you could represent as a design matrix, as a layer-specific spatial design matrix, that for every voxel has a range of layer contribution. So in this case, this voxel has 0 white matter in it, but 5% of layer 1, 40% of layer 2, 25% of layer 3, and 30% of CSF. And you can do that for every single voxel. Now, if you were to do that for every single voxel, then just like in a temporal design matrix, you could invert this model and say, right, I've got my voxel values, which is my fMRI volume. I regress that against my design matrix, and I've got my value, my signal intensity for layers 1, 2, 3, and just for free, I get the white matter signal and the CSF signal with it, right? Now, there are a couple of issues here. First one, it is quite something to actually be able to set this up. Well, I don't think I'm going to tread in great detail, but basically, the Weiner paper, from the Leipzig group, described a method in which you can do this relatively easily. In my tools, I re-implemented their method because I didn't manage to make Pilou Bazar's tools work on my data. So I re-implemented it in my toolbox. So the volumetric layering and several of the preceding functions do exactly this. The volumetric layering sets up this design matrix. John, please.
So the Weiner paper, the paper that describes the volume.
Yes.
So Well, sorry, I missed. What did they set up? They
Right. So right. You're right. I wasn't quite complete there. What Miriam's paper did was setting up a mathematical framework of the level set method to make to calculate the equivolume depth. Now, what I did in my paper about the spatial GLM is the next step to make that conversion into layer-specific contribution to a voxel. But that last step is relatively trivial, right? Okay. Right. So they mainly used it. A level set is not a description of partial volume directly, but exactly that's the extension that we go. Yes. Please, by the way, ask if anything is unclear about this. Anyway, there is the question of how to set up that matrix, but let's just for the moment assume that can be done with some of these functions. One of the very important assumptions that you're making is one that John already mentioned this morning. You're very explicitly assuming that every single voxel in your region of interest indeed is this linear combination of the layer signal. So if your region of interest has a difference in general intensity, then this breaks down. If your region of interest has several histological regions in there with different betas for different layers, this breaks down. So there are several quite strict assumptions here that if you do not adhere to those assumptions, the inversion of this model might be problematic. Now, often throw in, isn't that the same assumption that very often is used anyway? I'm very curious what you think about that. Whenever we do layer-specific analysis, well, we would like to say something about the signal in a region of interest. So we're averaging anyway. So we're thereby implicitly assuming homogeneity of the layer signal over that region. Yeah, please.
I guess the more voxels we use, the
less. Well, is it? That's a good question.
This is essentially under
No. It's overdetermined by a wide margin because you're only estimating 5.
Right, but I mean, if you assume spatially different betas, then it becomes under.
Right. Yeah. Sure. So you're absolutely right. What we have done in our paper that was published only like half a year ago, we managed to set this up and see how this performs. Well, our conclusion was that if you simulate data without a lot of noise, then this clearly outperforms other methods of obtaining layer signal. But in the presence of noise, this inversion gives rise to artifacts that, may be so problematic that the results can hardly be trusted. Now, an interesting question is if those values can't be trusted, then basically that means that this formulation is incorrect. And if that formulation is incorrect, well, can any other way of obtaining layer signal from that region of interest, can that be trusted? Something to think about. I don't necessarily have an answer there. Well, you already gave a potential solution. This is a very simple formulation. What you could do is try and add more, more prior information to the system. And that can be a spatial, something about the spatial homogeneity. You mentioned something about regularization terms. Those are all ways of optimizing spatial regression like this. So I'm not saying that it's impossible. I am saying that I tried some of these and we didn't have a lot of luck. If you have suggestions, then I'd be happy to hear it, but also please feel free to try it out. Having said that, I do think this is a very interesting way of looking at the same problem. As opposed to the classic way of just interpolating along a line. It also goes back to one of the questions we had this morning about nominal resolution. Cheryl, what came out of that little list of nominal resolutions? How did people like to define it? That's it.
The problems with any true resolution or nominal?
Both. So,
sad news is this morning there was a station 2 that I think didn't get attended that had the true resolution question on it. Yet offered an opinion on true resolution. We're going to still have another mixer with these sheets tomorrow morning, so that's okay. So all I can report back on is the nominal resolution, which everybody felt like. 0.8, maybe 0.7 would be like odd numbers.
Oh, right. But then you're talking about a number. Well, yeah. The interesting question you can ask is, all right, how many layers do you need? How many layers would you be able to obtain from this? Because one of the inputs in this method is the number of layers that you want to get out. Whereas if you just interpolate along a line, you can interpolate 3 times, 5 times, 100 times, doesn't matter, right? Because whereas if you're actively trying to extract and separate the signals, this needs to be something that you think about beforehand. Well, our experience is that with like 0.8 millimeter data, which is also what I just showed you, 3 layers is that could work. More is not really going to work. As soon as you have like 5 or 6 layers, then you see those artifacts to be so clearly visible that, well, it's end of story. Nothing to be, nothing informative will arise from that. Let's see. Yeah, please.
To get into this discussion, what is the nature of these side effects? I still don't understand why.
Right. Okay.
How do you know
basically, inverting a model very quickly gives rise to basically it's what happens when you invert a model that is wrong. You're amplifying the noise, but you're amplifying the noise more than you're extracting the signal. I find it hard to explain in really well adequately, but as you can imagine, all these regressors are very correlated because one voxel here already is spread over 4 layers. So what you might know from temporal regression as well, if you have 2 stimuli that are very close together, in principle, it is almost impossible to know where the signal comes from. So that is a problem of collinearity. Well, these columns of your design matrix will be very collinear. And as soon as you've got collinearities, in the inversion of the model doesn't really know to which bin the signal should be attributed.
That depends basically on the orientation of the cortex relative to the grid size.
Yeah, yeah,
So,
absolutely. Yeah, so if this grid, well, clearly, if you go towards infinite resolution, so very, very tiny voxel size, then every voxel is only in one layer, and thereby you only have ones and zeros, and then you've got an orthogonal matrix, and therefore no collinearity, and thereby a perfect estimation. Right? I hope that gives you some intuition for why this goes wrong. Are there any questions, John? Please.
Yeah, so I like your comment. Yeah, we see this point that the conditioning of the system, is going to vary also, across poles as well as you say. In a given place, you may see the conditions will change depending on the size of the voxel. But the point you made a few minutes ago was interesting. That is, you said that this framework seems to potentially be the best. I think you had said for 0.8 millimeter voxels, in which you're trying to separate out layers. And since the cortex is about 2.5 millimeters thick, it seems that you have 0.8 millimeter voxels. That basically, there is about, on average, 3 voxels across the cortex. And so what I like about that idea is that you're not trying to use this inversion, or at least what you just said is that you're not trying to use it to kind of perform super resolution per se. You're just trying to unmix the signal, right? It seems that you could almost separate out 3 layers with but this technique just gives you a little bit better unmixing of the signals without really trying to take your 0.8 millimeter voxels and try to infer layers that are 0.4 millimeters thick. Trying to separate out 6 layers from those data. So I kind of like this idea that it's able to perform a little bit of a mixing without being so aggressive as to form super resolution.
Yeah,
that's a great point.
So that's indeed our rule of thumb, approx, that, well, if you have a cortical thickness of 3 millimeters and a resolution of 1 millimeter, 3 divided by 1 is 3 layers. That's sort of the ballpark that we're using. It's only an estimate, and it still really depends on, because you can also think of configurations of a cortex in which your system would still be collinear. So that's why I also like what you said. There is not just the resolution, but also the way in which your gyrus is folded over your voxels. Because the more different that is, the more power you have of unmixing. And we're still in the process of figuring out how many layers we can obtain. Anyway, are there any more questions about this? Because one of the things I would really like to show is a way of what your next analysis could be. Because we've always had a bit of a problem in the layer community. If you indeed have 100 interpolations right there, then it's very difficult to do adequate statistics on that. Because every, 1/100th of an element is very similar to the previous one. And it's a very difficult question how to analyze that. But now, suddenly, we only have 3 left. And then we were like, right, well, now we can just do our, something much closer to the classical way of statistics. Let's see, these are still some boxes around the different parts of the pipeline. I was just talking about this, right? So this way of thinking about extracting layers has consequences for your experimental design as well, because we were asking ourselves the question: how many degrees of freedom do we need in our task, for example, and how can we obtain informative data from any experiment? And our conclusion was that we would ideally be interested in the triple interaction of a bottom-up effect and a top-down effect and a layer effect. And with bottom-up and top-down, I now just mean stimuli that to which the cortex responds differently on a layer level. So just to give, as a short refresher of statistics, a triple interaction means two different double interactions in this case. So this triple interaction would mean that the bottom-up effect interaction with the layer is different from the top-down effect with the layer, right? So then suddenly it seems very sensible that this is something you look for. But then your experimental design clearly needs to be able to, well, to disentangle a bottom-up effect and a top-down effect. And you would need to be able to measure that layer specifically. So that's what we tried in our visual attention task. Basically, without going into great detail, we hypothesized that a top-down effect, like a visual stimulus, would activate the middle layers, and that if you also pay attention to something as a top-down effect. Oh, sorry, the stimulus effect is clearly the bottom-up effect because, well, from the eyes it goes via the thalamus to layer 4. It would go to the middle layers. The attention effect would be the opposite. It would go, at least it hypothesized to go to deep and maybe top layers. And if you subtract those, let's see, if there is an attention on condition and you can subtract the stimulus on and off conditions, you would have a pure stimulus effect, which would only give you the middle layer. You would theoretically get the same for the off condition. Well, vice versa for the attention effect. If you do, well, attention on minus attention off in both conditions here, you would get an attention effect. And maybe on top of that, you would even get an interaction effect. Well, I can go through the details of my design, but basically it just means that we showed people gratings in 2/3 of the case, so a stimulus effect, and no grating in 1/3 of the effect. And we asked people to attend either to the right side, in this case, indicated with the circle, or to the left. So that we could manipulate both attention and stimulus. And what did we find? Well, as we expected, we found a very strong stimulus bolt response, and that was even stronger when there was attention directed to that retinotopic location. And when there was no stimulus presented, there was still that attention effect, but it wasn't, well, as clearly visible and also not as clearly bold response. Right, and we did this study in V1, V2, and V3. These are some statistics over subjects, but that's not incredibly interesting. The interesting is what we didn't find at the layer level, because what we did subsequently is for these conditions, so stimulus on, stimulus off, attention on, stimulus and attention off, we for V1 and V2 and V3, we wanted to know, all right, is there indeed a different layer effect for every layer bin? And basically, the only thing we found is that every layer towards the superficial layers responded a bit more strongly. And that was it. What I'm trying to say is that this was layer specifically an epic null result. That triple interaction we did not find. Let's see, some statistics, but that's not very important. But that is something I also wanted to share with you, that we felt that we did a pretty decent study here. Is there anything specific?
You're just getting this off your data.
Okay, yeah, sure. But
You're
that
the data man.
That we did a decent study here to figure out if there was a layer-specific response in a very clean 2x2 design, and we didn't find anything. So we're still trying to publish this, but that's one of the things I wanted to throw into the group as well. What do we do whenever we have a null result? Because cry. That's one thing we do. But there is the question of, well, there are some published studies about layers that actually find an effect. But I know people in this room and the other room that basically performed the same methods and didn't find anything, and that those data sets ended up in the file drawer. I think that's a shame. I think the file drawer problem is a very big problem for the layer community. Now, one of the solutions, I believe, is, thank you, Cheryl, hosting this meeting, so that we get more idea of what's in those file drawers and what we are trying to do. But I also think that people outside of this room, well, have the right to know about that. So I would like to propose to also try and show your null results here and there a bit more often and try and put them into the literature, please.
Also, so we have a project, and we have a maybe slightly different or maybe similar problem with defining what a null result is actually. Because is it not also because of, for example, all the vascular and rain effects? Isn't it also interesting if you don't find a difference in the different layers? If you find activation values similar over the layers, and you assume that there should be some integration effect between the layers, and then you don't find it because you have the same activation in place. So basically, even the null result of a layer interaction could actually be an actual result. So that's
sure,
kind of different
but then
from other fields where no difference means nothing, and here your assumption is that you would find a difference because of the vascular effect.
So yeah, that's one of the things. We do find a vascular effect, but I agree with you. I wasn't very explicit a moment ago in explaining what I meant by my null result. I would like to find something over and above only a vascular effect. So what we do find is towards the surface, I think you still wanted to discuss which axes should go where. Well, in my case, that is activation and towards the superficial layers. So we do find this increase towards the superficial layers, and we find it mildly for an attention effect, clearly for a stimulus effect. But ideally, you would like to find something over and above that. So in terms of, for example, that triple interaction effect, it was a null result. That doesn't mean that we don't find anything at all. We do find the stimulus and also the layer by stimulus and the, I think by heart, I think you also find the attention by layer effect. But then indeed the question is that interesting enough to publish or not? Well, I hope so. Yeah, John.
But I was just going to say, I was just going to, yeah, get to the funding. What's the null? And the null is that flashing checkerboards, you say activation across all layers, creating a fold, you expect this.
Yep.
The question is this slope different from the null? Right. So
Yep.
if the null is a slope and you're seeing a flat slope,
Yeah.
that's a yeah. The point is, how do you define a control experiment? That
Yeah.
defines the null. You know, I mean, have a null experiment where you don't expect to measure that response, and then contrast that slope.
Yeah.
But defining that null.
Statistically speaking, I would say it's easy to define the null, but it is difficult to find to define what a meaningful deviation from that null is, right? Yeah.
People still arguing what should you expect to see across steps in response to flashing check.
Sure. Okay. So yeah, I agree. There is this null or not? I think it is reasonable to expect an increase towards the PL surface. But if that is, for example, linear dependent on the actual amplitude of the stimulus effect, that's a lot larger than the tension effect, I don't know that. And that's a very good question to which I don't have an answer. So the overarching point thereby is, what are we looking for? What does a good statistical experiment look like when you're doing a layer analysis? Now, in case of Renzo's phaso, for example, he very clearly hopes to find this V-shaped response. Because as soon as you've got that, well, you're reasonably certain that there is that it isn't just blood flow effect, because, well, it could go down, maybe, unless you've got a theory on why it would. So.
No, I agree with you. It's experimental design. Experimental design is extremely important. How would you come up with a control system, with which to compare
Yeah.
That's important. But yeah, people do things like p-tests. So, well, is the activation significantly higher in this layer versus that? I don't think that's appropriate because of the coupling. So yeah, no, you're raising a good point. I see people try to do presentation tests. There's a lot of different attempts that try to quantify. When you see that, are the slopes different? Yeah, it's not really clear that there's consensus. But experimental design is hugely important. How do you, because I think what you want to do is, not just sort of measure inverse slope compared to something else, and see they differ. Like for your acquisition, for your voxel size, for your echo time, what slope would you expect to see if there's no null? And how would you compare that slope against what you see in your metric? And that's another. That slope is going to vary.
So there are some very clear results that would be interpretable, like that V, but if it's not that, then what is interpretable? Well, that's difficult. So overarchingly, especially in this meeting in general, we're discussing the pulse sequences here right now, the analysis, but there is also the experimental design, and we as physicists aren't always the best people to think about that. So I would advocate to, try and set up together with psychologists as well, to really think about, what is the way to conduct a good experiment there. Anyway, by the way, also the results for this are all online, because one of the things I tried with this paper is saying, right, I don't know the answer. I think it is a null result, however you define that. But if we can't really know what well, what should come out and what is meaningful, then at the very least, let's try and be sure that everybody else could do this and could repeat it as easily as possible. So for this study, I made sure that there is this entire graphical pipeline that automatically generates your code, for which you can replace modules easily if you think it's more appropriate for your experiment, or if you're more fond of a different implementation. But if I check out this file on GitHub, there are also some Jupyter notebooks. Who's heard of Jupyter notebooks? Okay, like half. They're Python notebooks. They're little Python files, but they're very easily inspectable in the browser. So if I click on an IPython notebook file, then you can very easily see, right, these are the Python imports that I did. These are the well, the hemispheres and the different conditions, and blah blah blah, statistics, Python, more statistics, and a lot of pictures. So with this study, we try to make everything as openly available as possible, thereby to give you a way of starting an analysis, but also to just see end to end what problems well arise when you're trying to do this. To think about well, also these problems about experimental design that you mightn't think of initially when you're starting your experiment. How am I doing for time? I'm not sure if there is any.
On time, so it's about
Wow.
time for biological break. The other half of our class will join us in 15 minutes. Coffee has been refreshed across the street. But before you wrap, I've gotten to the point in my notes where I'm talking about surface-based analysis versus voxel-based analysis versus that fancy GLM. What is the right phrase to use when we describe that kind of regression?
Spatial regression, a laminar spatial regression.
So
that's how I call it.
We'll officially call it the laminar spatial regression.
Yes.
We need this thing that is neither voxel-based nor circle-based. We're not moving to the surface, we're not hitting the voxels. We're doing more nuanced laminar regression, laminar spatial regression.
Yeah.
All right, that's our word for it.
Yeah, I like it. All right, sure. Coming into the notes. So there are definitely some parts of the of this pipeline that I can show you if you're interested. My goal of this presentation was also to tailor it to what you are interested in. So first, I'm going to ask you: is there anything you'd like to see, to a part of the pipeline or a part of? Otherwise, I keep on rambling. I can do that. Yeah, please.
I would like to see, you know, now you have here on the interface, guys, I understand that the subject folder is basically the same version of that. But basically, if you say that you have to disk, then it looks like on the.
Right, it's a very good question. So I decided before this, in preparation of the presentation, to not go too much into the application because we wanted to talk about layers. But if you're asking about it, hey, so
I'm at least curious to see
so
once how this how
sure,
this runs, and
we'll do.
The different tools are working happily together or not.
Let's see. There are two things there. One is just how to adapt this application and what would my workflow be? Is that the question? Or is it more like how to?
Intuitive from the maybe, but I'm curious more about what is under the hood, like what is actually happening there in MATLAB. I think it's starting in MATLAB. So
right. Okay, that's a good question. So the toolbox that I wrote is contains a lot of very modular functions. So those are all every function here. It's actually got a link to a MATLAB file in the toolbox. So the toolbox that in MATLAB that we installed is this one. And
So I think
that-
as a group, we did not go through this.
oh, right. No, sure. Sorry. That's a
Once
good point.
you get into MATLAB and you launch
Yes.
this one install of, which I know some of you guys did while we were setting
No,
up.
Thank you
Gives
for.
you access to a bunch of MATLAB scripts. And then that graphical interface has generated this master script.m, which is in the subject 11 location. So I think the answer to this question is the MATLAB functions that are being called, that are part of this toolbox, are spelled out in this master script.
Yeah, that's good. She explains it better than me. Sorry about that. The reason is that
I have the back seat. It's easier from the back
and
seat.
I'm mixing up the previous presentation with this one.
Yeah.
So yeah, we didn't go through it. Let's do that for a moment.
We are on break. And so
oh crap!
this is our life.
Oh.
But I'm going to
Yeah.
steal some coffee from over there. And so let's end the formal
Thank you.
presentation. Anybody else who needs a break and a drink of the on-campus type? If I have coffee. Yes. So coffee
love
break. Anybody who's dedicated and wants to stay in the room and walk through this with you and get their hands on it more, stay. I will come back with some refreshments, but we need to mix it up a bit so we can get on with our schedule.
Yeah.
In about 15 minutes.
Sure. Sounds good.
Keep going. I will do my best to come back here.
Please don't feel embarrassed to leave. I'm very quickly going to go through this, and then I'm with you, Alicia. So let me quickly get rid of this and execute and remove FSH.